Okay, so that's when a finite volume starts to come in. Well, we kind of already talked about like how does a nonlinear PDE develop discontinuity. It's basically the waves travel in different directions. If they go away from each other, that's actually no problem. It's called a rarefication wave. And the problem is that the waves actually collide and a discontinuity would form. I mean, if the waves collide and there is not enough viscosity to smooth it out, then a kind of a discontinuity would occur. Mathematically, it is only a true discontinuity if viscosity is equal to 0, but for all practical purposes, we can't really resolve this really smooth curve with grid. So you can forget about the difference between a true discontinuity and an approximate one. So let's analyze a little bit more about how does this particular equation develop this discontinuity. In particular, we want to see, we have previously used the characteristics, right, to analyze the behavior of the solution. Does that still hold over here? Can we still say that we have these characteristic lines that are traveling along which the solution is constant? Right? Before we said that we have these characteristic lines where we have a time and space. Along each line, we can derive the slope of the line such that the solution stays constant along the line. To many people's amazement, this still works for nonlinear PDEs. Except for that, the slope of these characteristics are no longer going to be the same, right? For our linear advection equation, the slope depends on the big U, which is either positive or negative. So everything either goes in parallel towards the right or in parallel towards the left. So in this case, we no longer have parallel lines because now the slope of this is delta t, delta x. My delta x over delta t would be equal to actually my small u. The lines in this particular case are still straight lines because if the solution doesn't change value along this characteristic line, which means u doesn't change value, then dx over dt doesn't change value. That means the slope is constant along the line if the solution is constant. And the fact that the solution is constant can come from a chain rule the same way as before. So if I have a line on which the slope dx over dt is equal to u, then if I look at the function u of xt and t, if you take d dt of that, it's actually going to be the left-hand side of this equation. Is partial u partial t plus partial u partial x using chain rule times dx dt. And if dx dt is equal to u, then this is equal to 0, right? Going through that very quickly, but like you can basically use chain rule to figure out that the solution along the line is constant if the slope of the line is equal to the solution value. So what does that mean with respect to our previous case if u is equal to cosine of 2 pi x? That means when u is positive, the slope is positive. When u is 0, the line goes straight up. And when u is negative, the slope is negative, right? So if we look at our previous case, here, from 0 to half, u is positive. From half to 1, u is negative. And when u is equal to 0 or 1 or half, u is equal to 0. So that means at these three locations, the lines goes straight up, right? This is when dx over dt is equal to 0. That means dx is 0. That means the line goes up. Now, in this region, u is greater than 0. This region, u is less than 0. in particular, U has maximum value at 1/4 and 3/4. So this is where the lines are steepest. This is going towards the positive direction, and here is going towards the negative direction, right? And elsewhere, the lines are less steep, like that, and approaches a vertical line here. Also, the lines are less steep over here, and right? You have a question?
Isn't our why is it 0 at the why is it straight up at 0?
It's I actually draw the line of a u equal to sine. So actually that's not right. So this is not our previous solution. Our previous solution is actually u equal to cosine of 2 pi x. I'm sorry for that. So basically you would shift the domain by a little bit. I would just erase that and say this is actually 1/4, right? This is 3/4, and come on, 0 is over here, and I have my 1 over here. So u is greater than 0 here, u is greater than 0 here. So I have waves going towards the right again over here. Right, so with periodic domain, that's what the picture would look like. It's lucky that cosine x is just a phase shift from sine of x. All right. Okay, so this is half. So that's actually why I think we have a discontinuity at here, which is 1/4, right? Of course, finite difference doesn't actually do properly the discontinuity, but that's where I expect the discontinuity to form. That's because starting from 0, u is equal to 1. Starting from half, u is equal to -1. And the solution is expected to be constant along this line. So the value of the solution at this point should be simultaneously 1 and -1, right? Actually, that means the way we are analyzing differential equations doesn't actually work anymore, right? We have been using characteristics which depends on the chain rule, and the chain rule only works if the u is actually differentiable. I mean, at this point along this discontinuity, this doesn't work anymore, right? You only talk about derivatives if derivatives actually exist. So all the stuff we have been doing about the PDE only works in the smooth regions of the solution. Along the shock waves, we need to figure out something else. Okay, and that something else is actually no longer a PDE, because in order for you to actually write down that partial differential equation, you have to actually write partial u partial x, which is infinity. So this doesn't make any sense along this continuity. So what do we do here? Well, this, yes? What is flipped?
Why is the t on the y-axis?
Why is the t on the y-axis? Because we are looking at a space-time diagram of how the solution evolves.
Yeah, but wouldn't that be like if you're looking at the slope of dx over dt, shouldn't it be x at time?
Oh yeah, the slope here, yeah, that's a very good point. This is actually not really the slope, but the inverted slope.
Okay.
Right, the slope, the reciprocal of the slope is dx dt, which is equal to u. That's why when u is equal to 0, the line goes straight up, right? So it's actually calling it a slope is actually not exactly right. Okay, and to just drive the point home a little bit more, if you do a contour of t x t u, you actually well, I think I should specify the contour levels to be length space of -1 to 1 to let's use 50 contour lines. Yeah, so this is when other than the non-physical region created by finite difference, here is actually where you see the characteristic lines, right? So this is the lines on which the solution stays constant, and as you can see, they are pretty straight lines. And here is when they collide together to form this discontinuity, which generates these oscillations in finite difference. We're going to look at a proper contour plot when we are able to solve this correctly. All right.